Ever sit in bed at night wondering how that terrible sound and that lightning bolt is made? Ever wonder why you got a shock from touching that doorknob or car handle? Ever wonder why your hair wants to hang onto a brush? Ever wonder why your socks get stuck together when they come out of the dryer? Well, it's all about static electricity. All of these photographs are displays of the after effects of static electricity. So, want to know exactly what static electricity is? Well, static electricity is the accumulation of an excess electrical charge on an object. Now, back to that night and thinking about the lightning bolt. How does static electricity happen? What's going on is that a stationary electrical charge is building up on the surface of a material, like seen in this picture. When two materials rub together, one material is left with a positive charge and the other material is left with a negative charge. The two newly made charges are attracted to each other, and that is when we are able to observe static electricity, as shown in the following pictures. The balloon will stick to all types of walls as well. The reason for this is that the neutral object is polarizing. When a charged object gets near the uncharged one, it attracts all of the opposite charges closer to the charged object. Before we go any further, let's check out some basic information about an atom. Atoms contain particles called protons, neutrons, and electrons. Protons and electrons have a property called an electric charge. Neutrons have no electric charge. Electric charges, now pay attention because this is very important. There are two different kinds of electrical charges. Protons have a positive charge, electrons have a negative charge. For now, you don't have to worry about the neutrons because they don't have a charge, so they aren't really important to static electricity. So what's happening in most atoms? Atoms contain an equal number of protons and electrons. In this example of carbon atom, it is 6. So the positive and negative charges cancel out, and the atom has no net electrical charge. Objects with no net charge are said to be neutral. Most objects and the atoms that they are made of are neutral. So back to the question, where do charges come from? In materials or atoms, if electrons equal protons, the atom will be neutral. If electrons are greater than protons, it is gaining electrons, so you'll get a negative charge. If electrons are less than protons, it is losing electrons. You will end up with a positive charge. Some materials or atoms are more willing to gain electrons, and some are more willing to lose electrons. So how does the electric charge happen? Wait, first you need to know a couple of terms like what is an insulator and what is a conductor. Some materials called insulators hold their electrons more tightly than others. Insulators such as plastic, rubber, wood, and glass do not conduct electricity well. Depending on what it is made of, some insulators hold onto the electrons more tightly than others. Conductors allow the electrons to move freely. Conductors let go of their electrons instead of holding onto them tight. Silver, copper, and gold are excellent conductors. Okay, but remember that we just jumped from an atom to materials that are made from atoms. Okay, let's review this. The objects gaining the electrons become negatively charged. The objects losing the electrons become positively charged. This is an example of static electricity, which is the accumulation of excess charge on an object. Coming clear yet? Let's continue looking at more information about static electricity. Static electricity is accumulation of excess electrical charge on an object. Okay, got that? Now, when electrons are transferred from one object to another, the total number of electrons remain the same. This is the law of conservation of charge. Electric charged objects obey two rules. Opposite charges attract, like in picture A. Like charges repel, like in picture B and C. Another important thing that you need to know is that an electric field surrounds every electric charge and exerts a force that causes electric charges to move. Remember, this is an important thing, that static electricity. An electric field surrounds every electric charge and exerts a force that causes other electric charges to move. Just to keep things interesting, you need a couple more terms, conduction and induction, and they both have to do with transferring an electric charge. The process of transferring a charge by touching is called charging by conduction. This is like rubbing the balloon on the sweater, picks up the electrons, and then can be picked up by a neutral paper on the table. The rearrangement of electrons on a neutral object caused by a nearby charged object is charging by induction. This is like if you have a charged brush and bring it near your hair but don't actually brush it. Your hair will move, but when you take the brush away, your hair will fall back to normal. Okay, remember the lightning bolt question? Well, we are finally really answering that now. When a buildup of electric charge is released, a static discharge is said to occur. Static discharge is the lightning bolt, or the shock from the doorknob, or the crackle as you pull apart the stuck socks. And the thunder, well, that sound is the displacement of air molecules, but that is another totally interesting science lesson. Okay, everybody, we just learned a lot about static electricity. Let's watch some really cool science experiments about static electricity and see if you can figure out what's going on from what you just learned about static electricity.
Frostbite Theater presents Cold Cuts, no baloney.
Just science.
Hi, I'm Joanna.
And I'm Steve.
And this is a piece of PVC pipe.
And this is a plastic cup that has a hole drilled into the bottom of it. So when I fill it with water, it leaks out of the bottom.
If I charge the pipe and then bring it close to the stream of water, the water is attracted to it. That's because water molecules are polar molecules.
Water molecules look a little bit like Mickey Mouse. The two hydrogen atoms are bunched up on one side of the oxygen atom. And while the molecule itself is neutral overall, it has a positive end and a negative end because of the way it's shaped. Molecules, like water, that have an asymmetrical distribution of charge are called polar molecules.
Let's say the pipe has a negative electrical charge. If I bring it close to the stream of water, the water molecule flips so that the positive end is pointed towards the negatively charged pipe. Opposite charges attract, so the water is drawn towards the pipe.
This is an experiment you can do for yourself at home fairly easily. All you need to do is turn on the faucet so a little bit of water comes out. And then you place a charged object near the water. Any object that'll hold a charge will do, like a comb.
Or a balloon that you've rubbed on your head.
Or a plastic pen.
Thanks for watching. I hope you'll join us again soon for another experiment.
This made kind of a mess.
It really did. Let's see, make this work better.
But it's
There
just
we go.
water.
That's true. Hi, I'm Joanna,
And I'm Steve.
and this is a Van de Graaff generator.
And these are bubbles.
Have you ever noticed that you tend to get shocked less in the summer by static electricity than you do in the winter? That's because usually there's more moisture in the air in the summer than in the winter. Since water molecules are polar, they are attracted to and carry charge away from charged objects.
Now, we can't see the water molecules in the air, but we can use the bubbles to figure out what they're doing. When the Van de Graaff is off and uncharged, the bubbles behave just as you would expect them to.
When the dome is charged, things change. The bubbles are attracted to the dome. Some of the bubbles pick up charge in the air on their way to the dome. If they pick up enough charge before they run into the dome, they'll be repelled by it. The bubbles fly away, carrying charge with them.
There's less moisture in the air in the winter, so that's like having only a few bubbles in the air at one time. The dome holds its charge longer because there are fewer things taking the charge away from it.
In the summer, there's more moisture in the air, so that's like having a lot of bubbles.
Oh.
Allow me. The more moisture that's in the air, the faster the dome loses its charge. Thanks for watching. I hope you'll join us again soon for another experiment.
Bubble fight!
I think I'm losing.
Superior firepower does not ensure victory.
They're coming back at me.
What'll happen if a person were to touch it? Or maybe a better question is, should a person touch it? Well, maybe yes, maybe no. Do you guys know what voltage is? What does voltage measure? It's actually a measurement of energy per charge. Do you know how many volts are in a flashlight battery? One of those D cells? 1.5. Very good. How many volts in a 9-volt battery? 9. Yeah, that's why they call it a 9-volt battery. How many volts come out of the wall? About 120. How many volts on that? When that thing's running well, that's about 200,000. Okay, so think about this for a second. Can you safely touch a flashlight battery? Yeah. Can you safely touch a 9-volt battery? Yeah. Can you safely stick your finger in the outlet? No. So if you can't touch 120 volts, should a person touch 200,000? Yes. Probably not, but you want to see it anyway? Yes. That's what I was afraid of. So, first, before we do this, I know it's not on. But there is something I am on that I don't want to be. The ground. What's this? Stool. Stool made from? Which is an? I'm going to get on the stool. Not because I'm short, but because I want to get away from the ground. Right? If I'm down here, the only insulation I have is whatever's in my shoe. Not that much. If I'm up here, I've got my shoe, and I have 9 inches of plastic? Something like that. Hopefully, it's enough insulation, the electrons won't flow through me and into the ground. They'll just gather on me. If they just gather on me, what should happen? What hair I have left should stand up. Yes. 3, 2, 1. Ah! Doesn't hurt. Anything happening? I'm hoping hair is doing something. But at any rate, I'm not dead, which is a good start. Right? Now, how many volts are on my left hand? How much is a bunch? About 200,000. What'll happen if I touch the dome with my right hand at the same time? Nothing. Why does nothing happen? How many volts in my left hand? 200,000. How many volts in my right hand? 200,000. What's the difference? There's no difference. Electricity flows from high voltage down to low voltage. If it's the same voltage, it doesn't move around. It's like having a bathtub full of water. If all the water is at one level, the water stays put. Have you ever seen birds land on the power lines? They don't get killed. Same reason. Both their feet are at one voltage. They might get a little bit puffy, but they don't get killed. Now, what would happen if instead of this dome, I touched the grounding dome with my right hand? How many volts would be in my left hand? 200,000. How many volts would be in my right hand? Ground is 0. Defined as 0. What's the difference? 200,000, that's like a waterfall. Okay, the electrons will flow from a high voltage down to a low voltage. In fact, if you listen carefully when I point at the dome, what's that sound? Yeah, those are electrons flying off my finger. You'll notice, watch my hair when I point. Why does my hair go down? Yeah, if the electrons are flying off my finger, they're not on my head to make my hair stand up. And you'll notice it also doesn't do it when I make a fist, but it does when I point. It turns out charges jump off of points easier than they jump off of rounded things. That's why these things are round, is to gather the charge. You know what a lightning rod is? What's a lightning rod? A pointy piece of metal. People think it's there to attract lightning. It's actually there to bleed charge away so lightning doesn't strike. In my pocket, I have that nail. It's like a lightning rod. If I let go of the point, if your ears are good, you can hear it whistling. If your eyes are good, you can see when I cover the point, and I let go of the point, my hair moves up and down. Don't know if you can see it, but I can feel it. I can feel it moving. It's more obvious, though, instead of pointing at the audience, if I point here. Okay, so again, why is my hair going down? I'm losing electrons. The electrons are flying off the nail to the dome. And if I get it close enough, we can actually make a little spark that we can see better if Mr. Dave turns the lights off. A little spark. Lights back on. So that little spark tells you something. For there to be a spark there, the electrons have to come from the dome through me, out the nail to that dome. If electricity is flowing through me, why am I not dead? I'm not insulated. That's the ground. I'm touching the ground. I'm not disappointed. I'm just confused. Why am I not dead? Well, I mean, if you like, I can come down here. What's my hair doing? Nothing. Where are the electrons going? Through my feet into the ground. If I get up here, I block them. So electricity was flowing through me. Why am I not dead? Again, this is not a major disappointment on my part. But why am I not dead? You know what current is? Like in a river, what does current tell you? Yeah, which way and how much. Okay, which way is the water flowing and how much water is flowing? For electricity, what does current tell you? Which way and how much. Right, is this a high current or a low current? It's low. That's why I'm not dead. There's just not that much electricity flowing through me. If this were a high current, what would happen? Yeah, I die in kind of in a gross way. Have you ever put the hot dog in the microwave? Ever forget to poke holes? What happens if you don't poke holes? It blows up, right? Because the water inside changes to steam and it needs to get out somehow. Well, if this were a high current, the same thing would happen to me. My blood would boil, and I'd blow up all over the room, which would be an experiment you only do one time. It's also why you don't stick your finger in the outlet. Okay, even though the outlet's only 120 volts, it's a high current. And it's really the current that gets you, and not really the voltage. Now then, what'll happen to my hair if I let go of the dome? Stay up, mostly. How come? I'm insulated. I'm insulated. There's nowhere for the electrons to go except from the water vapor in the air. If I want to get rid of it quickly, what do I need to do? I need to step off. And as soon as I step off, I get a shock through my foot, and the electrons lead me that way. By the way, this is how a lightning rod works. Here's your thunderstorm. You have a lightning rod. You bleed off the charge, lightning doesn't strike. Your neighbor doesn't have a lightning rod. They get fried. You're fine, they're not. You're fine, they're not. So that's a little bit about charges and electricity, and again, it's why our machine works in the